So just a very short recap for what we have seen in the previous lecture. So now we all know understood what is a bilevel optimization problem. I've shown you some example with a stress on linear bilevel problem. And also I introduced two important concepts, that is the induced region. So this is the set of solution of the first and second level problems that are feasible with respect to all the constraints, and such that the y, so the decision of the second level, are optimal response of with respect to the x, the variable of the first level. So this is an important concept, and also the other important concept is the h-point relaxation, which is the set of solution vectors x, y that satisfy all the constraints of the first and the second level. So if we optimize the objective function of the first level in the high point relaxation, we obtained, for instance, a lower bound is if it's a minimization problem, it's a relaxation, okay? So these are useful concepts that will also be used in this lecture now. Also, I put a stress on some modeling issue. So it's very important to really understand the fact that the second level sees only the constraints that are in its problem. All the constraints that we call coupling constraints, so that involve x and y variables, so first and second level variables, but that are in the first level, those constraints are not seen by the second level. And it makes things different, and you have to be careful to really understand what you want to model with your bilevel problem. Okay, so this is these are different things that I discussed in the first lecture. I have a couple of things I still want to say in general regarding bilevel optimization problem. There is one issue I didn't talk about yet, which is the situation when the second level has multiple optimal solutions. This is something that can create difficulties, and also you have to understand the consequences of your decision. So I will illustrate this with a very simple example that is here. You see this bilevel optimization problem. So the first level optimizes on x, which must be non-negative, and the second level reacts by choosing a value for y, and y must be between 0 and 1. So when you look at the second level, given that x must be non-negative, as long as x is smaller than 1, so between 0 and 1, the optimal value for y in the second level will be to take y equal to 1, because the coefficient here would be positive, okay? And when x is bigger than 1, then the optimal value of the second level is 0, because the coefficient here becomes negative, and the second level is a maximization problem. So that means that if you look at this in this the graphical representation, you have here x in the horizontal axis, y in the vertical one. And so when x is between 0 and 1, the optimal value for the second level is 1. And then when x is bigger than 1, the optimal value is 0. But when x is equal to 1, in fact, any value for y between 0 and 1 is optimal, because the coefficient of that multiply y in the objective function is 0. So you have here, when x is equal to 1, you have a whole segment of optimal solution for the second level, okay? And so how to solve this problem? Well, in fact, you may consider what we call the optimistic option, which means that the optimal solution, if in case of multiple optimal solution at the second level, the one that will be chosen is the one that is the most in favor of the leader. So here, this would be the optimal solution, because when x is equal to 1, the best option for the leader is to have y equal to 1 as well, because then he gets a profit equal to 1. Okay? But there is the other option, which is the pessimistic option. The pessimistic option is that in case of multiple optimal second level solution, well, the one that will be chosen is the one that is the less favorable for the leader. And in this case, this would be the solution here. Now, the problem, of course, there is this raises an issue here. Because if you think about, you look at the pessimistic option, this is an open segment here. You see, and the optimal solution of the problem is never reached because this is an open segment. So this is some difficulty that appears in case of pessimistic situation, and you have to be very careful to understand if which is the situation that is the real one. If it's the optimistic one, this is good because automatically the model react in this way here, because the first level chooses in case of multiple solution for the second level, the first level will choose the best for itself. But here you are in trouble, you see? So this is something that is important and you have to pay attention as well. Okay, and a last thing before focusing on linear bilevel is just something I would like to mention in the examples I have presented in the first lecture, mainly regarding pricing problems and regarding Stackelberg security game. You may have several followers. Of course, you may have several leaders, several followers. Here in my lecture, I focus on one leader and one or several followers. Didier will talk much more about that, so I just want to mention this. And so when you have multiple followers, you may have, let's say, two very different situations. You may have the case where they are independent, in the sense that each follower faces an optimization problem that depends on the first level decision variables, but not on the decision variables of the other followers. Okay, and this is, for instance, often the case of pricing. The decision of the different potential buyers are not influenced by each other. Well, you may have situation where it does, but this is another story, let's say. But you may have also the situation where indeed those followers are dependent. And that means that each one faces an optimization problem which depends not only on the first level decision variables, but also on the decision variables of the other followers. And for instance, there are problems, for instance, in the energy domain, for electricity markets, for instance, in which you have indeed followers which, in fact, which it is assumed that the second level corresponds to a Nash equilibrium between the different followers. You see? And Nash equilibrium is typically a problem like this. You have a Nash equilibrium when the optimal decision of each follower is optimal when the other one are also at the equilibrium. So these are two different things that I just would like to mention to open. I open here different windows so that you see the variety of different aspects that you can express with bilevel optimization, and it may raise very difficult problems, in fact. Okay. So after now that I'm done, before just going to linear problems, here is just a list of basic references. I would say I put them by chronological orders. So the first one is a bibliography, is a survey by Luis Vicente and Calamai on bilevel optimization. The second one is, I would say, the reference book on bilevel optimization by Stefan Dempe. This is, I think, for somebody who wants to study or to do research in bilevel optimization, this is the reference book. And there is another book, I didn't put it here, by Jonathan Bart. I'm sorry, I forgot it. Which is more practical oriented, I would say. Then there are two additional surveys, one by Colson, Marcotte, and Savard, which was published in 2005. And the last one is a survey I wrote with Alessia Violin on the relation, the approach of bilevel optimization for pricing problems. Okay, now let's go to linear bilevel problems. So just to remind, here is the general formulation of a bilevel optimization that in which everything is linear. So X is the vector of the first level or leader variables. Y is the vector of the follower variables. Here you have some coupling constraints that are in the first level, which means I remind you that the second level is not aware of those constraints. And then the second level has an objective function that depends only on the Y variables. And you have here again linear constraints. Okay, so this is the general formulation of a linear bilevel optimization problem. Okay, the first thing I say that, well, one may think that these are the easiest problem, this is the easiest class of bilevel optimization problems, but it is already hard. And just to give you an idea, this is an observation that was made in a paper by Charlodet and others in '97. In fact, one can see that 0-1 linear optimization is a special case of bilevel linear optimization. So in the sense that you can model the condition, the binary condition or on a variable X, so the fact that X can take only value 0 or 1, you can model this using a bilevel reformulation. In the following way, what you say is in the first level, you have the constraint saying that V must be equal to 0. And also you have the constraint saying that V is the optimal value of this very simple linear problem. So this is your second level problem, okay? And the second level problem is depicted here. It's easy to understand graphically what it is. So you see what you have is that the feasible region in the second level is this triangle. Okay, you have the first constraint here, you have the second constraint here, and here you have the non-negativity for W. So this is the feasible domain of the second level. In the second level, you maximize W. So the set of optimal solution of the second level, depending on X, is given by this upper part of the triangle, okay? But in the first level, you have the constraint that this W must be equal to 0. So the inducible region is the intersection of this kink and this line here, which means that the inducible region is made only of two values, 2 points, this one and this one, which is exactly the same as saying that X must take value 0 or 1. You see? So any binary condition on the variable, you can model it by adding this constraint here in the model, and you add a second level, which is this one. So linear bilevel optimization is at least as hard as binary linear optimization. So we are done. Just one thing to remark is that, in fact, what happens is that this is, I make a link with the previous lecture. You see, I was talking about those coupling constraints, and here this is exactly what happens when you put these constraints in the first level. This is a coupling constraints that, in fact, make the inducible region disconnected. You only have those 2 points now. Okay, so in fact, this observation was made by Audet et al. And in the paper by Hansen et al., they provide a formal proof of the fact that linear bilevel programming is strongly NP-hard. And what they do, they reduced the problem known under the name of kernel. They reduce this problem to linear bilevel programming. A kernel is to find, you are given a graph, and you want to find a subset of vertices that are independent. So, so that there is, none of them are linked by an edge. And all the vertices that do not belong to the kernel must link by at least one edge to one node of the kernel. So it's a kind of set that dominates all the rest. And so kernel and finding the question whether there exists a kernel in a graph is a problem that is known as strongly NP-complete, that it reduces to linear bilevel programming. Okay, that implies also, of course, because binary linear programming is a special case of MILP, it means that MILP is also a special case of linear bilevel programming. So we are in a, that means bilevel programming is a really hard class of problem. There are more complexity results, and I think maybe Ivana will talk about that regarding bilevel optimization, but I just stop here because I focus on linear bilevel programming. Okay, so now we know that somehow this is a difficult class of problems. So far, I haven't said anything on how to solve those problems. And the first thing to solve those problems is important is to understand a bit more about the structure of the optimal solution to get some properties. And so in the previous lecture, I showed you some very simple bilevel linear optimization problem graphically. You remember it was this drawing like a little house, huh? And in fact, what I showed you were examples of the first and the second property that are here on this slide. The first property is that the inducible region is the inducible region is always the union of faces of the high point relaxation. So I will go back to my drawing here. Okay. You see, if this is the high point relaxation here. Huh? This is the high point relaxation, the feasible domain of the high point relaxation is the set of points that satisfy all the constraints of the first and the second level. And it is clear, of course, that an optimal solution of the problem must be one of these, must belong to this high point relaxation. And in fact, it must be also a vertex of it. You see here, when you think about the fact that you must be in the high point relaxation and to be feasible. In addition, you must, the solution must optimize the second level problem. Must be an optimal solution of the second level problem. Given that the second level problem is an LP, it means that the optimal solution of the second level will be a vertex of this LP polyhedron, okay? And this, so that means that in fact, the optimal solution of the whole bilevel optimization problem will be a vertex of the high point relaxation, okay? And so this is a very important property, as we are going to see. This is something that we can exploit from an algorithmic point of view. And also another thing that we can remark here with, for instance, with this simple graphical representation, it's that if, imagine that I have no coupling constraints. Okay, so this was the previous example, I think here. Yes, I have no coupling constraints. In this case, the inducible region is made of faces of the high point, the polyhedron, which is the high point relaxation domain, feasible domain. So it's made of, it's a part of the frontier of the high point relaxation. It is made of a collection of faces of them. But of course, here we see that this is not convex because you have those here, the two faces is the union of two faces which constitute this kink, okay? Here we have no coupling constraints. Here I have a coupling constraint. What happens is that now I keep this property, my inducible region is made of the union of faces of the high point relaxation, but it is not necessarily connected anymore. So if you do not have coupling constraints, the inducible region is connected. And if you have coupling constraints, the inducible region may be disconnected. But it is always the union of some faces of the polyhedron corresponding to the high point relaxation, okay? And in addition, the optimal solution of the problem is a vertex of the high point relaxation, okay? Now, very nice, we can exploit these properties. You see, this is what I say. The inducible region is the union of faces of the high point relaxation if it is connected, if there are no coupling constraints. And if the problem is feasible, then there exists an optimal solution, which is a vertex of the high point relaxation. And so this observation, these properties has been exploited by Bialas and Karwan and by Barth to develop an algorithm to find an optimal solution of linear BP, which is called the kth best algorithm. And the idea is to to start with the high point relaxation, you optimize the, so you minimize, assume we consider a minimization problem. So you minimize the first level objective function under all the constraints. So in the high point relaxation, you obtain a vertex. If this vertex is the optimal solution of the second level, then you have the optimal solution of your problem and you stop. If it's not the case, the idea is to look at all the neighbor vertices, so all the vertices of the high point relaxation which are neighbors of the incumbent, and to iterate. And also you can introduce some these are just the general idea. So you see, you go from vertex to adjacent vertices and so on, and you can use some lower and upper bound that you can develop, because the high point relaxation, the first solution that you obtain gives you a lower bound, and then by for the given solution X that you obtain, you can find the optimal solution of the second level, and this gives you a feasible solution to the linear BP. So this gives you an upper bound, and you can exploit those bounds to accelerate the procedure. Okay, so this is the very general idea of what is known under the name of the K-best algorithm. Now, this is, so far, this exploits what I would call the primal world. We are here in, we have the variable, decision variable of the first level and the second level, and you look at vertices in the high point relaxation. Now, there's another thing, and this is another pathway, let's say, to approach bilevel optimization, which consists in reformulate the problem into a single level one. Okay. So the idea is to try to eliminate this optimization problem that is in that represent the second level optimization, and try to translate the fact that the Y is the optimal solution of a second level via some constraints, some other constraints, and by introducing some new variables, which are, in fact, the variables corresponding to the dual of the linear problem which constitutes the second level. So the idea is to exploit duality. In linear programming, we have indeed this extraordinary, powerful tool that is duality that we can exploit here. I'm presenting this idea of reformulation for linear bilevel because I concentrate on that. But in fact, as you will understand in a minute, you can, the same idea, you can exploit it provided the second level is convex, because the idea is to exploit optimality conditions, so-called KKT, Karushkun-Tucker optimality conditions. Okay? So the idea is to reformulate the problem. So here, you have here on the left, the bilevel linear optimization problem. And I have here associated to, to the constraint of the second level, I have put here in parentheses a vector lambda, which is, so the vector of dual variables corresponding to all the constraints of this second level. Okay, just one thing here I would like to stress. So the second level is, in fact, has an objective that does not depend, of course, on the first level variable. The first level variable, they appear here in the constraints of the second level. So each time that you have different values for the X variable, you have a different feasible domain here. changes. This is just some remark. So now lambda is my vector of dual variables. Now, what we know is that we can, we have this tool of duality for linear programming, which means that you can translate the optimality condition of Y by saying that there exists a vector lambda of the dual, satisfying the constraint of the dual of this linear program, such that the complementarity constraints are satisfied. Okay, so now if you look at this, the dual, if I look at the formulation of the dual, I would maximize lambda times b minus cx, and the constraint in this dual would be that lambda d must be smaller than or equal to f. Okay? Sorry, lambda d must be equal to f, because I have, I do not have non-negativity constraints on the y. So you see here, lambda d equal to f, these are the constraint of the dual of this LP here. Okay? Plus, of course, the non-negativity constraints on my dual variable lambda, since they correspond here to inequality constraints in the primer. So these constraints are the constraint of the dual of this LP, and the constraints here are the complementarity constraints. I remind you the complementarity constraints, what they mean is that each time either the constraints is tight, so it is an equality, so this is 0, or the corresponding dual variable, the lambda I corresponding to that constraint, is equal to 0. Okay? So I can reformulate the condition saying that Y is optimal for that LP by saying here, well, I have also a vector lambda satisfying those constraints, and such that I have those complementarity constraints that are satisfied. This is equivalent, okay? And in this way, now I have a single level optimization problem. Very nice, good. Yes, but of course, this does not solve our problem. Because if you look at these complementarity constraints, they are of course the difficult ones, because you have variables x, y, and lambda, which means here that those constraints are nonlinear. Okay? But if you forget those constraints, if you relax them, and you look at what remains here, in fact, you have a problem in which you have those constraints here, and then you have constraints, you have the dual, but those two problems are completely disconnected, okay? And lambda is just a feasibility here. The lambda do not appear in the objective function, and the two group of constraints are completely separate. These are really the link between the two worlds, the primal and the dual world. So if you relax them, in fact, what you have is nothing else than the high point relaxation, because you can forget lambda, provided that the dual is feasible. I mean, you don't care of it. And what remains here is just the high point relaxation. These are the constraints of the first and the second level, and the objective function of the first level. And now, so the idea is the following. You can, well, this has been proposed by Ansel et al. In '92, is to develop a branch and bound for solving this problem by branching on those constraints. Okay, at the beginning, you relax them completely, which means you solve the high point relaxation. If the solution of the high point relaxation is such that y is optimal for the given x, you stop, you have the optimal solution. Otherwise, you find a feasible solution and you have an upper and lower bound. And you look at those constraints and you choose one of them that is violated. You branch on it. So you define two problems. On one, you set lambda equal to 0. On the other one, you set dy minus b plus cx equal to 0, and you iterate. You see, you have an upper and lower bound, and you can derive a branch and bound algorithm with those ingredients. Okay, so this is one possible approach. And then later on, Audet et al., they proposed a branch and cut for solving this problem. And in fact, they have, which means that they add cuts. And mainly what they do is that they, so when you look at the high point relaxation to start with, so this is the problem. And then, good question. Sorry. the inequality they add are Gomori cuts, which means they introduce 0,1 variable to model those disjunction here. And so I cannot tell you in details like that exactly how it works. I encourage you to look at their paper, but this is the basic idea, is to develop those Gomori cuts, which are mixed integer Gomori cuts, because you have the x and y and lambda variables are continuous, and they are in addition those 0,1 variables that are introduced to model this disjunction. Later on, also Audet and others, they also published a paper in which they derive also disjunctive cuts based on those complementarity constraints, but they never implemented them. I just got the answer this morning, by the way. I wanted to know whether they tried them or not. Okay, now this idea also has been exploited in a different way. You see, I mentioned the introduction of binary variables here, because what Hansen et al. Proposed was a branch and bound. And at that time, they implemented the whole branch and bound by themselves. But nowadays, one have a tendency, at least one likes, to use software, optimization software, and because they are very powerful, and it's a great advantage. So also there is, you may think, well, there is a way to reformulate this to obtain a mixed integer formulation of the problem. And indeed, so here on the left, what I put is just this single level reformulation. So you see these the constraints of first and second level, the dual constraints of the second level, and the complementarity constraint. Now, you can reformulate this by using 0,1 variable in the following way. You see, the idea is to use what we call big M's. And so for each disjunction, so here this is you have for each constraint here you have a product. So you have in fact the I y minus bi plus cix time must be equal to 0. And so each such disjunction, you can model it by introducing a variable zi, and zi will be equal to 1 if lambda I must be, oops, equal to 1. Where am I? Oops. Yeah. Sorry. Now you see, if zi is equal to 1, to 0, sorry, that's push lambda I to be equal to 0. If zi is equal to 1, this terms now vanishes, and it push cx plus dy to be smaller than or equal to b, given that from the constraint in the original model, this must be bigger than or equal to b, you force this equal to 0. Okay, so this is if zi is equal to 1. If zi is equal to 0, you are going to force lambda I to be equal to 0, which means that you always satisfy this. Because you have lambda I must be smaller than or equal to 0, given that it must be non-negative, you're done. Okay? So this is, but of course, you need now those big M values. The big M is a constant, and you see here what it means. For instance, if zi is equal to 1, okay, that means that you must satisfy the second constraint, this cx plus dy must be equal to b. But then it means that md must be an upper bound on any possible value for the lambda I. If so, md must be big enough. If md is extremely large, you're done. But what does it mean, extremely large? Huh? This is really the issue here, and the same thing for MP. Usually, if you look at the second constraint, so MP should be big enough to ensure that when you want to relax this constraint, this value is not, this expression cx plus dy is not going to reach something that is bigger than b plus mp. So mp is an upper bound on the maximum of cx plus dy minus b when xy is feasible. Usually this upper bound exists for those constraints because the x and y usually are bounded. They are in your model. For instance, imagine these are production levels or things like that. Usually you have bounds on x and y. So that means that you can determine a bound that on cx plus dy. But for the second level, for the dual big M constant, this is a different issue. And now, so, okay. Now, also, the idea that was used for a while is the following. Given that when you have some value for the big M that is valid, any value bigger than those values are also valid. And so for a while, especially in the energy domain, there was a procedure that was used for determining those big M. This I refer to a paper by that we will see just in a minute by Pineda and Morales. And they were, in this paper, they mentioned that in the energy domain, at least, to determine those big M, it was frequent to use a trial and error tuning procedure, which is the following. you choose some value, some arbitrary values for MP and MD. So the big M for the primal condition and the dual condition. And then you solve your MIP. Huh? You solve this MIP. And if some big M, I will explain what it means, appear in some active constraints, then they iterate. And they iterate until this does not happen anymore. And what is this? What does it mean some MP or MD appear in active constraint is the following. Now, I take the example here. If imagine that, so you solve, I choose value for MD and MP. I solve this MIP. So I obtain a solution in which Z has always 0 or 1 values. And imagine that Z is equal to 1. Zi, a certain Zi is equal to 1. And that the lambda in the optimal solution is then equal to MD in this solution. Then that means that this constraint is tight in this is MIP. And the idea of this trial and error procedure is to say, maybe it's because this MD is too tight that lambda takes this value. So I will increase it and see whether it happens, whether I get a solution, because if when I increase it, if lambda is not tight anymore, then this means that this lambda should be big enough. So what they do, each time that Z is equal to 1 and that lambda is equal to MD, they will increase MD and iterate. Or for the other case, if when lambda is equal, when Z is equal to 0, if the constraint is tight at the optimal solution, then they will increase MP and iterate. And they do that until none of those constraints is tight. And then they think, okay, I'm done. I found my optimal solution and my big M's are good enough. And interestingly, in this paper, Pineda and Morales, they show a very simple example with 2 variables in which they show that this trial and error method is wrong. And so the example, I just did a cut and paste from their paper. So this is the example they provide, okay? So you see it's a linear LP. You have 2 variables. X is the variable of the first level, Y the variable of the second level, and you have those constraints. Okay, there are no coupling constraints, by the way. Now here, you have 2 constraints in the second level. So 2 dual variables. And so you can rewrite the second level here on the right. So you see I have here the constraints of the first level and the constraints of the second level. Okay. These are the constraints of the dual of the second level. You see I would have exactly, where are they? Whoops. Well, they are written here. This is, I have only 1 constraint for the second level. Yes, because this is the variable of the first level, so it should go on the right-hand side. And that means that you have only 1 constraint here in the dual of the second level, and you have no negativity constraint because here you have inequality. So this is your second level domain here. Okay. And then the complementarity constraints are written, you see here, by using those big M. And now here there is something interesting, is the following. If you look at the second level dual here, sorry, here, it is a segment because you are in the non-negative orthant, it must be positive, and you have these equality constraints, so it's just a segment like this, the positive orthant, just a small segment. And so it is bounded. And what happens is that they show, so it is bounded, it is a segment, and you are sure that lambda 1 and lambda 2 can never be bigger than respectively 1 and 100. Now, they show in this example that if you take big M's with the following values, so this is for the primal, so far so good, but for the dual, you see, you take a value that is here, that is smaller than the maximum value that lambda 2 can take. Okay? In this case, if you take those values, what you obtain is you solve the MIP with those values, you obtain an optimal solution that is not optimal, and in fact, those values, the optimal solution, I mean, those big M satisfy this trial and error procedure. There is none of those none of the constraints involving the big M is binding in the optimal solution, so the procedure stops. But you have here, in fact, you have values for the big M that are not valid because you are much too constrained. So this is one first thing. Even if you have, this procedure is not good first. But in addition to that, here we are lucky because you have a dual that is bounded. Okay. But now if you look at the reformulation I had here, okay, because I choose, just for you to remark, a bilevel formulation in which here I have only inequalities. So in the dual, what I have here is variables, the dual variables must be non-negative, and the constraints are all equality, okay? So my dual of the second level is just lambda d equal f and lambda non-negative. Okay. Now, what happens is that this domain of the dual is often unbounded. And in fact, this is a presentation comes from a paper that I cited just after, that I did with Thomas Kleinert, Martin Schmidt, and Frank Plain, and recently, and in this work we are doing on linear bilevel, I think Thomas has tested most of the problems that are in libraries available have indeed dual that are unbounded. So, because what you need here for the big M on lambda is in fact is a bound on the maximum value that lambda can reach in a feasible solution or in an optimal solution. Okay, and this is the issue here. You see, so let's concentrate on a bound for those dual big M. So assume that now we have here, we say, okay, we know well enough our problem to be able to find big M that are valid for this group of constraints, which is often the case. Now I need to concentrate on those big M, which would be upper bound on the value of lambda. of each dual variable of the second level, okay? And so the difficulty, first, this trial and error doesn't work. Second, often this region is unbounded. So because you might think, oh, but this is easy. This is just a polyhedron. And to find an upper bound on lambda, I can maximize any objective function on this polyhedron, and I get the big M. So far, so good? No. It does not work, because if D2 is unbounded and if you didn't choose well your objective function, you simply go to infinity. This doesn't tell you anything. And in fact, what happens is that it's a bit more subtle in our situation, because we are in the case of bilevel optimization, linear bilevel optimization. So when we have seen this reformulation as a single level, what we know is that, well, XY is feasible, must be feasible for the high point relaxation. Lambda must be feasible for the dual, for this, okay? But in addition, in fact, lambda must be the optimal solution of an LP on this, okay? Because of the strong duality, lambda star is the optimal solution of the dual of the second level, which determines Y, okay? So, and the advantage is that here lambda, okay, it is in an unbounded polyhedron, but when we consider an optimal solution, it means that lambda is an optimal solution of an LP, but lambda is also finite. So it is the optimal solution of an LP on D2, which means that it is a vertex of D2. And so the situation is that you have a polyhedron D2 that is often an open polyhedron, okay? But what you need is an upper bound on the value on the coordinates of the vertices of this polyhedron. If you have this, you are done, because you know that in an optimal solution, lambda will always be a vertex. So you need an upper bound on the coordinate of the vertices of your polyhedron, okay? And this is, in fact, what we have done recently. We have considered this, and interestingly, what we have shown, in fact, is that verifying whether a big M is valid, in fact, is a difficult problem. What we have shown, so let's first formulate the problem. So the problem valid MD is the following. So we are given a matrix A, vector B, and a value big M. And what the question we have is the following: is M a valid upper bound on the ith coordinate of every vertex of the polyhedron defined by this system of inequalities, AX smaller than or equal to B? So this is the question. This is really this corresponds to determine this MD. If we can do this for each coordinate, we take the biggest big M and we are done. So the question we raise here, so the problem we consider is this a valid upper bound on the ith coordinate of every vertex of the polyhedron? And what we can show, in fact, is that this problem is strongly co-NP complete. So just a little parenthesis from a complexity point of view. In fact, to answer a yes answer to this question is a nasty question, because if you want to, if the answer is yes, it means yes, every vertex has a coordinate, a ith coordinate smaller than m. And to have a certificate of this question, this is difficult, because how are you? It's easier to say no. The answer to no is easier, because if the answer is no, it means no, there is a vertex for which for which xi is bigger than m. And the proof of this is simply you need to exhibit just that vertex. So it's a short proof, it's a concise answer. But here, this is why it's in co-NP, because to say that, to prove that no vertex violates this is much more difficult. So the problem is co-NP complete, which means that it's complement, which in which the question is the complement. So does it exist a vertex such that its ith coordinate is smaller than m? This problem, we prove that it is NP complete. Okay, so this means that to wrap up this story is that, well, this approach of here to solve the problem is a MIP is not really feasible, in the sense that if you have no information regarding your problem, if you don't know how to determine those big M, you cannot use this simply in this way. You can use, you can model the complementarity constraints as SOS constraints, and then you can use Cplex. I'm not specialist of this. I think you should ask Thomas or Martine. They can tell you much more about these different options, but this is the idea. I mean, do not use it in this way, it's wrong. Unless, of course, you may have problems for which you have some specific information regarding those dual variables, and for which you can derive again that are valid. But in general, it's strongly NPR, strongly co-NP complete. Okay. So this is the message, let's say. Okay. Now that we have done this, also there is still something about duality I would like to talk about that can be used for reformulation, or that can be used to strengthen the model. So I have shown this single level KKT reformulation, but you can write it in a different way. In fact, what you can use is strong duality, which is in fact totally equivalent, which means what? It means that in the single level reformulation, you have here the constraints of the dual of this LP, which is the second level. And here I add the strong duality, which says that the value of the objective function of the primal must be smaller than or equal to the value of the objective function of the dual of the second level. Because one thing that you know, you always have weak duality. If you have a solution that lambda that satisfies this, you have a solution y that satisfies that, you know by weak duality that the objective function here will be always bigger than the value of the objective function of the dual. So if you add the inequality in the reverse sense, you impose the equality, which says that you have strong duality. And so that means that they are primal and dual optimal solution respectively. Okay? So this is totally equivalent to then to use the KKT or complementarity constraints. You can group them and you get exactly the same thing. But it's a different vision you can think, and you could think, well, could it be useful also here to derive a MIP from this? Well, it is not so so nice, I would say, because here you end up with a constraint that are non-linear, because you have the product lambda cx here, when you use the KKT reformulation, you really have this disjunction that you can handle by using, where is it? Let me show you. Okay, here. You see, you can really handle this this disjunction here in this reformulation. Okay, you can reformulate it. You can try to linearize this, or you can use other approaches, but not so much. But these constraints here has another interesting feature. It can be interesting also to exploit it to derive some valid inequality to strengthen the HPR relaxation, for instance. So you see, you have this is this strong duality condition, okay? You see, it's just reformulation of that, nothing else. Now, you can derive a valid inequality linear, because this is a valid inequality, but it is not linear. This is, in fact, in the model, should be in the model. But the issue is these terms that are nonlinear, this expression here. But what you can do is the following. You see, this is the sum over I, let's say, of the lambda I time Ci x. And given that usually you have information on your primal variable x and y, and here x in particular, you can bound from below this expression. You can find a lower bound on that. For instance, you minimize this expression under the constraints that x, y, and lambda are feasible, so satisfy all the constraints that are in the model. So you look for the minimum, a lower bound on this expression. And then, using this lower bound, you can derive this inequality that is valid for the model, because this is smaller than that, which is smaller than that. Because this is a lower bound on this part. Whoops, I made a mistake here, it should be a lambda. Ooh, very sorry. This term is wrong. This should be lambda C minus. I am very sorry. Okay. This is one thing. Now, this inequality, you can add it at the beginning. When you have, for instance, if you want to solve your problem, you can add them to the high point relaxation immediately. And the advantage of doing so is the following. If you look at the high point relaxation, which is this, you don't have the lower one. This, as I explained already at the beginning, you have no link between the lambda world and the XY world. So at the beginning, it's very weak as a relaxation. And by adding this inequality, this valid inequality that we derive coming from this, you link the two things, you link the two worlds, and you strengthen the model. This is one thing you can do that is useful and efficient. Now, in addition to that, in fact, if you look at this strong duality condition, as I said, you have those nonlinear product here, a variable. This would be kind of Cij lambda I xj. And in fact, you can reformulate this using the McCormick envelopes in the following way. You represent this as a sum of terms Zi, and each Zi represent lambda I times this linear expression that is the sum of the Cij xj, sorry. And now, given that this is nonlinear, I'm not going to detail this. This is something that is very well known by people working on MI-NLP, for instance. You can determine lower bound, linear lower bound on the Zi, which are the following. And so you can relax this condition by replacing it by this constraint plus those two for each I. And here again, what you have is that Ci plus is an upper bound on Cix, so you can find it by maximizing Cix for X feasible. Ci minus would be the minimum. So to determine, you would have to solve an LP in which you minimize Cix under the constraint of your model. And here you have lambda I plus and lambda I minus, which are upper and lower bound on lambda. Now, at the beginning, as I told you, it's difficult because that means that lambda I plus would be an upper bound on the coordinate of a vertex again in the dual. And at the beginning, I've told you this is NP hard to do. So this idea is not very useful at the beginning, but when you solve your bilevel optimization problem using branch and bound, so you branch on those complementarity constraints at some point, because you fix some lambda to 0 or some constraints of the primal, you get more and more information regarding also the dual, because you get more constraints. And you may end up with interesting and useful lower and upper bound under those dual variables, and in which case reformulating this, well, relaxing this constraint by adding those constraints is useful and interesting. So these are rather new thing. We have finished this recently, and just to show you here, you have an illustration of the impact of those constraints. So these are performance profiles of branch and bound. The performance profile is the following. You have here the time, and here you have the percentage of problems in your set of instances. So the percentage of instances that were solved within the given time limit. So it increases, of course, and you see here, that means that after this maximum time, this is the maximum number of instances that were solved by using the branch and bound. Now here you have the cut and branch, in which, so you add just one cut at the root node, this first cut that I showed you, and you see how it improves. So when you add this cut, you are able to solve much more problems within the same time limit. So you increase. The higher the curve, the better it is, because you solve more problems faster. And so here you have the number of nodes in the branch and bound tree, and here you have the running time. So you have here the branch and bound without cuts, and you see here you have different options. You have the cut and branch, which is just adding the cut at the root node, only one, but already it makes a significant improvement. And then here you have two different options of branch and cut. So these are using the McCormick envelope. I think here it's every, the level, 5 levels of, in the branch and bound trees. And this is after 10 levels. So you see, the lesson to draw is that using this cut, at least one, is very useful as a strong impact, because it really, it links the two words. So it's really important to have, it makes a significant difference. Okay, so I think, yes, I am done now. I have 10 minutes left. And I'm done with bilevel linear programming. I had the second part about bilevel optimization problem with bilinear objectives. Maybe I will just give you 5-10 minutes about that to show you the commonalities that there are with the linear bilevel problems, and I think we will be done then. So price setting, as I explained already, is following. In the first level, you have a leader who wants to optimize, let's say, revenue, profit, and for which he determines a vector of prices. And then in the second level, you have one or several followers. Oops, sorry. Each one wants to minimize the price, or he has the price to pay for doing something. For maybe he wants to buy some product, maybe he wants to construct some building, well, whatever it is. And in fact, this tax vector is associated to a set of activities X, and Y is a set of, I would say, untaxable activities, or that represent some alternatives. You have here, in the case of linear constraints, you have a better view here. You see, the idea here is that the leader is maximizing the revenue. So you have, let's say, a set of activities. Activity I will have a level of tax Ti, and Xi will represent the level of the activities activity I that the second level chooses. So you may have some constraints regarding the tax. You want them non-negative or whatever you want, or not too high. You may put upper bound, lower bound, whatever you want. And here in the second level, the follower or the followers make an arbitrage between those activities that are taxed by the first level and other activities that are offered on the market or other possibilities. And so they optimize their own objective function. And you have here, you see, you have the price that come from the first level and eventually some other costs. And here you have nonlinear constraints. Now, a couple of things I will say about that. So this is a typical type of bilevel bilinear problem. You see here you have those products of variable coming from the first and the second level. What is different? In fact, it has some dual flavor, I would say, with respect to the linear problems. In the sense that if you look at the bilevel linear problems, the variables of the first level, they appear in the constraints, but not in the objective. It's the contrary. Huh? If you go here, you see in the second level, you have a linear objective that is independent of the first level variable, but you have the first level variable here in the constraint. And here is a total dual situation, if I can say, in the sense that now the objective depends on the first level variables, but the domain here is independent of the first level variables. It remains always the same. But they are, once the first level variable are fixed, they are both linear problems in both cases. Okay, so that means that first, because it's an LP, you can also use the KKT. You can exploit this, but the difference here is that you have bilinear objectives. So even the first level objective is bilinear, is nonlinear. So you cannot adopt exactly the same approach as for the linear problems because you have this thing that is nonlinear to start with. So what happens is many of the pricing problem, at least we have been working on, are such that the X variable here, you can assume that they are 0, 1 variable because they are decision variables. You buy or you don't buy. But the advantage is that the second level is, so you may think they are binary variables, so this might be an NP-hard problem, but most of the time, this second level is an easy problem. So it's a 0, 1 problem or a MIP, but for which that is polynomial, for which you have exactly the complete description here of the convex hull of feasible solution. So you can consider this in an LP, and in addition, somehow you can exploit the fact that those X variables are binary or integer, binary, and that means that there is a good way to linearize those products of variable to make it a MIP. So this is just a general idea. At the beginning, I gave you examples of pricing problem. I will stop here. You can always contact me to ask more questions, references, whatever it is. I just would like to finish, give you one slide of recap, and to conclude within the time, I hope. So what I have been trying to do in these two lectures is to give you a glimpse about bilevel optimization, what it is, what it can do for how you can model, what are the issues in modeling, and then I have also concentrate on a problem in which the second level problem is an LP. Mostly when both problems are LPs, then we have seen there is a good way for solving this kind of problem by using strong duality, reformulation. One has to be careful with the choice of big M. there are some other ways to approach the problem that would rather recommend it. And just to finish, there are different type of problem. For instance, those bilinear problems for pricing or for security, like Steckelberg game. You can also exploit duality in this case, but it's different. But there are some commonalities between the two things. But what I would like to say, maybe just to finish, is that I think it's a fantastic domain and full of interesting problems and nice. Okay, thank you. That was it.